we're going to put a data center on the space station, right? Now, all of a sudden, meteors become a legitimate risk. So these are things that I spend my time thinking about. What qualifies me to do that? Prior to working at Google, I worked for a fintech startup called Blue Matrix, and I was their CIO, CTO, CISO, a whole bunch of C names they threw at me. And I did everything from help them get certifications for their business, SOC certifications, ISO certifications, but also built out the data centers. I literally racked and stacked servers. I went into 4 data centers around the world. I still have some bits and pieces of them here. It's called a blade. This is a single piece of hardware. We'll take a little higher level look at that a little bit later on. Do have a master's in computer science, undergraduate in math, and a couple of patents in network security. So I think I know what I'm talking about. And if you have an opportunity to prove me wrong here, please do. I'd love to have a lively discussion, clarify things where I can. Okay, so with that out of the way, what am I doing now? I'm not going to play the video, but anybody's interested in Office Space, it is my life. What would you say you do here? I deal with developers who have a specification, and we sometimes go out to the customers or vice versa, and we try to determine if we should proceed with work. And so I give not necessarily an opinion, I help facilitate an opinion, because there's some people I work with that are much, much more skilled than I in their very, very specific areas of expertise. Okay, so enough about me. Let's get on to the first core topic, which is information technology deployments. What do I mean by that? It's a lot of words. Basically, any business or any person or any government or anybody that's using information technology, you're using computers. How do you deploy those computers? And so taking a step back from the cloud, because our topic today is cloud security, let's talk about the anti-cloud. What's not cloud? The most common, maybe some of y'all are familiar with this term on-prem or on-premise. You start a business, you go out and you buy your servers, you connect them up to your ISP, you hire a developer, they write the code, you run out of disks, you order some more disks from Amazon, you put them in your computer. Maybe you're concerned about backups, so you take your disks and you ship them to a friend in Florida. You say, hold on to these in case I have a problem here. So on-prem means you own the hardware, you own the software. You may virtualize it, which we'll talk about virtualization a little bit later. But the pros of this, you have complete control. You let into your building who you want in your building. But cons, incredibly expensive. When I was at that small business prior to this, the way we did things, it was a constant conversation with sales. How much money are we bringing in this year? And I would say, well, do you want your servers to be 10% faster or 100% faster? And they'd say, well, of course, I want it to be 100% faster. Okay, well, I need $10 million this year for my hardware budget, but we're only going to bring in $9 million in sales. I'm like, well, you're not going to get that then, right? Because I was constrained to buying sort of physical hardware to a degree. So on-prem, most common. A variant of this is bare metal. A lot of people will use this term. You're just like perhaps most of you have a laptop that you're sitting in front of, or maybe a desktop. It's bare metal. It's the metal. It's the processor. It's the disk. You have code coming in, executing, and something coming out, usually over a network, presenting a web page, talking to other businesses, etc. But a lot of companies can't afford or don't know how to even build a server. And so they'll go to companies like Dell, and they'll say, Dell, we want to lease some servers. Dell might say, well, you can keep them in our office or our place of business, or we can help you, we'll get to that in a second, deploy it somewhere else. So it's a little bit, you have a little bit less control, but you have more flexibility. You don't have to know how to operate hardware. Dell knows how to operate hardware. You let Dell do it. Somewhere between on-prem and bare metal, is colo. So there's companies that own data centers, and they're just big buildings where they have multiple connections to the internet, multiple ISPs, multiple connections to power grids, power grid A, power grid B. They probably have diesel generators or some battery backups. And you go in with your servers, you put them into a cage, and we'll take a look at a cage a little bit later. And they provide you the basic utility. A lot of times when you're using bare metal, you might be buying it from a company that's putting it in a co-located facility. But on-prem becomes very important. Especially if you're a very small business, you likely don't have the security in place necessarily in your office. You might not have 24-hour security. You might just have somebody during business hours. You might not have multiple ISPs into your place of business. You might not have multiple power grids. You certainly don't have a diesel generator with 4 days worth of fuel. So this is why we outsource some of that. And later on, we'll talk about something called IaaS. It's kind of close to what that is. Lest we forget, there's something called edge. A lot of times we push the compute out to, these things, to our phones, to our wristwatches, right? To a degree, we can do a lot of business by putting our compute close to the problem, right? And so you can gather your heart rate with your iWatch. You don't necessarily need to send that data out to a server somewhere in Apple's data center or even to a co-located facility. It can be done right on your device, right? So we have a lot of places to deploy IT that are not the cloud. So what is the cloud? So here's my first gamble of the course here. Dr. Williams said, we'll see how we get participation. Is there anybody here willing to throw up their hand or just start shouting out here? What is the cloud? Thought we had a maybe there.
Isn't it it's just non-physical holding spaces for data?
That's a very good answer. In a lot of cases, from your perspective as the customer, it's just this amorphous thing. It's like, hey, it's computers running somewhere, right? And so that's a good answer. Before we get into what technically is a cloud, we probably have heard of a lot of these, right? And usually we've heard of these things. They're called hyperscalers. And so that would be Amazon, which has AWS, Microsoft, which has Azure, and Google, which has GCP, which is where I'm oriented. And so we own a whole bunch of data centers. And why are these companies where they are today?
Google Cloud Platform, GCP.
My phone's listening to me. Why are these companies in the place they are today with the cloud? Well, they had to build monster data centers for the problem they were solving at the time. So Google was solving a search problem. So they built data centers all over the world. Amazon was solving a shopping problem. So they put data centers all over the world. And now these companies realize, well, wait a minute, we can do more than just our core capability of search. We can do more than just our core capability of selling products, right? So they had the infrastructure in place. And so what these companies did is they made things just a bit more generic. That being said, there's a lot of other clouds out there besides those three. Some of these clouds I would dare say, are specialized, right? You might go to Oracle because you are needing to do something in the healthcare space, and they have almost specific software, or maybe they have certain certifications from a compliance perspective that meet the needs of things like HIPAA. Then you have some niche providers. Arguably, the private cloud that I worked for, we had a bunch of racks and a bunch of data centers around the world. Joe Public couldn't come and use our data center, but pretty much any customer that we had could use them, constrained to what we wanted them to do. So before we get into cloud, we've heard of them. I think we can all agree we've all heard of Amazon. We've all heard of Google. We've all heard of Azure. If you haven't, I'm happy to have a longer conversation later about that. But these are clouds, okay? They're just big companies with lots of resources. What is particular about some of these big ones, the hyperscalers, is they have to concern themselves with something like this. This is in the news today. I don't know if anybody's been seeing this in like Business Insider and stuff. about how vulnerable is the internet to underwater cable attacks. This is a serious problem for companies like Google, Microsoft, and Amazon, right? Because we have our own cables, and they're used in some very unique ways. But if you're just going to lease rack space in a data center in New Jersey, they likely don't have to contend themselves with undersea cables. But when you're Google, you do, because maybe some of your customers store some data in Europe, and maybe they do their backups in the US or vice versa. So these are very serious concerns. All right. Putting on one hat, this is the most exciting thing to me. Putting on another hat, maybe you would consider this boring. But there is a very technical definition of what cloud computing is, what the cloud is. And there's a NIST standard out there, NIST 800.154. And it's actually a very quick read. There's like the first 3 or 4 pages is just like header information. But it gets into a proper definition. And then it talks about, here's my rule of 3 again, I guess. There's 5 essential characteristics. What makes up a cloud? What defines a cloud? There's 3 ways that a cloud can interact. Like the company that is a cloud can interact with customers. And then there's multiple ways to deploy it. So let's look at the characteristics of a cloud. What makes a cloud, as opposed to just, I have a server in my corporate office. I have a server in a co-located facility. What's different about the cloud? So the first characteristic is called on-demand self-service. So anybody at any moment of time can go in and they can start running a computer. They can start running a compute job. And so the analogy I like to use is, imagine it's kind of like a gas station. Anybody here can drive their car to a gas station and you can always get gas. You don't have to be invited. You can just show up and get the gas. And for the most part, it's self-service, right? You go up, you put the hose in your car, you get gas. The next characteristic is called broad network access. So a cloud is generally available over the internet everywhere. And so with respect to my gas station analogy, this isn't just a little gas station on the side of the road. This gas station is next to a harbor. It is next to a runway. It is next to a road that goes everywhere, the Via Appia or something, I don't know. And so you can utilize it from a lot of different places for a lot of different reasons. So it's broadly available. Arguably, a gas station is shared, right? Dr. Williams can drive his car. I can drive my car. Who else? Jordan can drive his car. Evan can drive his car, right? Everybody can go there and sort of use it. We kind of sort of share the gas, right? And I don't have to know you. You don't know me, right? But we're all kind of using the same thing. Analogy is a little wonky here, but I think it still holds. There's always going to be gas, unless it's 1970s, right? You can go into the gas station, somebody will send a resupply truck, and there'll always be gas. So with the cloud, there will always be more compute. You want more processors because it's Black Friday, Cyber Monday, you can have more compute. You're building the latest AI model and you need to store a petabyte of data, there's always more disk, right? Someone is actually going to put physical data, physical things in place for you to virtually access things. And the last point is measured service. Basically, you got to pay for it, right? So there is a way to say you are using this much storage, you are using this much bandwidth, and you are using this much compute. And it all comes down to, for the most part, cost of the utility. So how much are you paying for heating, cooling, air conditioning, electricity, right? That sort of stuff. But also, layered on top of that is somebody had to put that server in a rack. Somebody had to wire it up. You have to pay for that. Okay, so that's the 5 characteristics of a cloud. Then there's called service models. So the first model, maybe we've heard of this, is called software as a service. So think of things like Google Workspace as software as a service. Gmail, right? A lot of people have Gmail. You have Drive. Maybe you have Docs and Sheets and Slides, right? You can use those tools. To a degree, you can tailor them. You can even write some code in them to write sort of the equivalent of a macro. But for the most part, you can only configure Gmail so far. You're going to send mail. So that's software as a service. But in terms of cloud, a lot of the things that can be built are amazing, especially now that we think about AI and the way these tools are just rapidly escalating how quickly we can develop code, make decisions, be creative, etc. So I like to think of it not just as a gas station, but a gas station where you can also get a car and you can get a driver, and you can just say something like, I want to go on vacation, and it will figure out the vacation for you and drive you there. So this is sort of what software as a service is, right? Things are just done for you, customers use it. The next service model inside a lot of clouds is called platform as a service. So this is really the breakthrough with things like GCP and Azure and AWS, is where smaller companies can say, hey, listen, I don't have the budget, but I have developers and we need to write code. So imagine these folks can go into this cloud, into this gas station, and not just get gas, right? But they can build the car. They have the little components they need to build it. They can go to this aisle and get the seat, this aisle, get the steering wheel and put it together. And maybe they have customers that view them as software as a service, right? So you might be a company that's selling financial research. You might be using Google's device to store your research reports. You might be using Google's network to host a web page where people can come and buy your research, things like that. So that's the platform as a service, right? You're using somebody's big building blocks to build something unique, build your own SaaS. And then at the bottom of the stack is really infrastructure as a service. So things like Google will say, listen, you want to buy space in our data center? We will sell you it, either physically or virtually. We will guarantee you have this amount of CPUs, this amount of disk space. Do whatever you want, right? So the analogy here is like they're giving you the raw materials to build a car. They're saying, here's sheet metal, here's raw rubber, right? Make your own tires, right? So when we talk about clouds can do any of these things, right? So Google acts as software as a service for workspace. It acts as platform as a service for things like GCP, where you can set up your own compute node or your own web server or your own application server. And then infrastructure as a service, where they say, listen, we're going to give you the internet connection and the power. Everything else is up to you, right? You want to install Linux on that machine, be our guest. You want to install Windows, be our guest. From that point forward, customer, it's up to you. The last part to what makes a cloud according to NIST is the deployment models. So we have private clouds. A company buys rack space in a data center and they say, okay, cool, we bought this rack space. We can start up a whole bunch of machines and we can shut them down. We can plug in more disks, but it's private. It's just my shop. Then there's community. The best way I can sort of say what a community is, it's not necessarily public community, but think about like the city of Raleigh, right? Raleigh might say, hey, we have a gas station and we let the police fill up their car and the fire department and the street cleaners, right? All these different diverse customers can use the same gas station, but not the general public. General public can't go get their gas there, right? Sort of like invite only. Then we have public clouds. Those are the hyperscalers we talk about. Anybody can come and join these things, within reason. Some companies might say, yeah, we don't want to do business with this country, or we don't want to do business with somebody who didn't pass a background check, or we don't want to do business with somebody in a certain, thing, a business that we disagree with, right? But generally open, fair game. And then there's hybrid, and hybrid's becoming a real big deal, especially with like public sector. When I say public sector, I mean like governments. Ironically, DARPANET, which is the foundation for the internet, was to, divest risk, right? If something happened on the East Coast of the US, the Department of Defense still had a server on the West Coast or in the middle or in Texas or, up north, right? And then quickly they're like, well, wait a minute, government's like, we can't put all of our workloads in Microsoft. What happens if something happens to Microsoft, right? So now they got to sort of partner. We're going to put some stuff in Microsoft, some stuff in Google, some stuff in AWS, right? So these you could almost consider to be hybrid clouds, right? They all kind of just allow the general building blocks, but they're separate entities that play nice together. Okay, so in summary, what is a cloud? There's 5 characteristics to a cloud, 3 service models and 4 deployment models. So You can look at the slides to get more information on that. We'll do a little knowledge check in a bit. At the heart of the cloud, and it's amazing, virtualization is something that came out a very, 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 very long time ago. But clouds wouldn't be clouds without this. So the best way to think about this concept of virtualization, so this is a new topic here, is, we used to walk around with calculators. A calculator is a computer, right? And it did one thing: addition, subtraction, multiplication. But you couldn't send an email, right? It was a calculator. It was one device. Well, then somebody said, hey, we can build a general purpose device. These are ostensibly computers, right? And then we have phones, which is now a glorified calculator in a lot of instances. But what happens is we've virtualized the machine, right? So at the end of the day, that phone is just doing logical calculations, right? It's taking information from a network, doing a calculation, storing some data, and so forth. This is sort of called virtualization. At the end of the day, your processor on your machine is just interpreting zeros and ones and doing stuff with it. So now we sort of abstract it. Well, the concept of virtualization, specifically with respect to cloud, is saying, well, rather than have to run everything on a bare metal computer, why don't we write a program that itself is a computer? So when this program runs, the program thinks it's a computer. It thinks it has bare metal. It really doesn't. It's just a virtualization. It's a virtual computer, right? And so the idea is, why this is important is we have virtualization in operating systems in our computers, but now we're doing it at a much, much bigger scale, right? And we're doing it at a much, much more abstract scale. And we're saying, okay, listen, if I want to have a Linux machine with 256 gig of memory and a terabyte disk, I don't need an actual physical machine like this, right? I can write a program that says, okay, I have a section of my code that pretends it's RAM, right? It's a DIMM. I have a section of my code that thinks it's the processor that's here, right? And my code shares it. And it says, well, Dan's computer's running. I'm going to give it, 128 gigs of this 256 memory. And I'm going to give Dr. Williams the other 128, gig of RAM, whatever. And so we can time slice and we can share it. And then when Dr. Williams isn't using the computer, I can take over that space that he was using or that extra memory here. And maybe my computer runs a little bit faster, right? But virtualization is nothing new. It's at the heart of operating systems, but cloud leverages it tremendously. And from a security perspective, it causes some really big problems, right? So if this DIMM was running in a computer and my workload is going through this side of it, and Dr. Williams' workload is going inside of this, what happens if, Dr. Williams is doing stuff for the Department of Defense? And what if I'm doing stuff for my website, right? What happens if there's a hardware failure? What happens if this DIMM was faulty and now I can start seeing his workload and he can see my workload, right? Kind of a big problem. All right. So how do we think about this in the physical world, the virtualization? Well, at some point, we have a rack of servers, and those servers do different things, right? This is AI generated. You can see how great AI is sometimes with wording. You can probably check some of the spelling there when I asked it to help me generate an image for network compute and storage and virtualization. So it made some mistakes. So I caution folks for AI is a wonderful tool. If you don't have the fundamentals, you might look at this and be like, yeah, that diagram's great. I look at this and I go, ooh, that's really wrong. Imagine now you're spitting out code, right? If you don't know fundamentally what code it wrote, you might be making some catastrophic mistakes. I digress. So back to this. This is what a data center actually looks like. So the private cloud I used to operate, this is one of our racks. So I had a whole bunch of servers here, and the blades, the things that kind of look like this, they ran compute nodes. And so I could spool up hundreds, if not thousands, of Linux boxes to sometimes do very specific financial calculations. Then the other parts are called NAS, network attached storage, where we could store data. So a cloud at the end of the day, as I mentioned, is just a whole bunch of servers that do networking, they do compute, they do storage, and they do it in a certain fashion. And that's those deployment models that we talked about. So a knowledge check, we'll see if we get some participation here if the folks are up for it. When we think about the 5 characteristics of a cloud, so here they are: on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. Which one of these from a high, medium, and low is sort of critically dependent on virtualization? Which ones can't we do without virtualization? Well, I'll make some claims for our friends who'll be watching this on the video replay later, so they're not waiting too long here thinking there's a buffering problem. On-demand self-service. So virtualization is critical. If every time somebody needed a new server, a person had to go into a data center and install a new piece of hardware, or they need to put another DIMM in, it wouldn't be possible. Broad network access. Virtualization is not really concerned with network access, but ironically, a lot of virtual networks take place. So if I have one physical machine, I might want to have a network of 100 virtual computers that are in isolation from 100 virtual computers. And so the work necessary to do that virtual networking could be substantial. Resource pooling, very, very high. It's Black Friday, Cyber Monday. We need to have a whole bunch of servers waiting to go. Again, I don't want to have to install them in a data center. I want to be able to virtually start them up, shut them down, save power on whatever comes after Cyber Monday. Rapid elasticity, same analogy here. Black Friday, Cyber Monday, I need to start ramping up more servers immediately. Maybe slowly from October through November, I need to increase the amount of web servers I have to handle more traffic. But man, come the end of November, I got a lot more servers just waiting to go. Come January, I want to power them down so I'm not paying for electricity and heating and cooling and all that stuff. Measured service, not so much. I can tell how much compute I'm using, how much network I'm using, how much storage I'm using, whether it's a virtual machine or not. Alexis, is there a question?
Yes. So in terms of the resource pooling and the rapid elasticity, would that be relevant for situations like I know recently there was the Mike Tyson fight on Netflix, and I know people were facing issues with like their network service. So would the resource pooling and rapid elasticity play a role in how people are able to, I guess, get really good service from Netflix and other platforms similar to it?
Yeah, absolutely. And I'll be very curious. I hope Netflix becomes transparent about what happened in that situation. But 100%, Netflix makes the claim, and I believe this to be true, that the fight was the most watched streamed event ever. Right? Well, they needed a lot of computers running. They needed to ship a lot of data around the world. Right? That costs money. Right? It's what it all comes down to. It costs money to have these servers running. And so they don't need that, at 3 o'clock in the morning in the US, right? Maybe most people are asleep. They needed it at 9 to 11, right? When everybody's watching the fight. But when that fight was over, they needed to shut everything down. The question of what actually went south with them will be interesting, because I know they're spooling up to host the NFL, I think, on Christmas Day. I hope they work out the kinks, because I don't think you want to catch the ire of a enraged football fan. Mike Tyson, I think we had a lot of armchair boxing fans. I was one of them. I enjoyed watching it, but I wouldn't say I watch boxing regularly. So, but yes, 100% rapid elasticity, resource pooling was 100% needed for Netflix. Mm-hmm.
Okay,
cool.
Thank you.
Yeah. So what's really going on in the cloud? Fundamentally, this is it. There's a bunch of physical machines out there. Companies own physical machines that have hardware on it. They have compute, they have storage, they have networking. And then somebody wrote some programs, very popular ones called VMware, which says, I'm going to write a program that pretends to be a physical machine. And someone can call a method or a function on that and say, add disk, add RAM, add network capacity, whatever it is. These virtual machines, oh, they think they're real machines. You know, I think you might insult a virtual machine if you're like, you're not real hardware. What do you mean I'm not real hardware? They think they are. They walk around, they act like they are. They think that they have hardware. I'm in that mindset because I worked in a cloud, but they truly do. There's really no difference to your, you write a program and you run it on bare metal, and you write a program and you run it on a virtual machine. If the people who wrote the virtual machine did their job correctly, it will do exactly the same thing. It will operate exactly the same way as it does on bare metal. Not always the case, but that's the goal. All right, so with that, what's really going on in the cloud? You have all this stuff that's happening in other business. So that's the image on the left. And the image on the right, there's control panels. And you as the human, you as the customer, you can set up your virtual networking, your virtual storage, or as this image says, store rack. And then maybe you have a view into the physical hardware as well. You know exactly where your servers are running. Are you running it in Seattle, or are you running it in Idaho, or are you running it in New York, or are you running it in Europe? I hate to be this base, but what's really going on in the cloud? Businesses are writing checks to cloud providers, who are in turn writing checks to data centers. And so this is why the hyperscalers exist. And this is their competitive advantage, because they don't have to write that check to the data centers. They are the data centers. They don't have to write a check to somebody with an undersea cable. They own the undersea cables. Okay, so that's our big foundation of IT deployments that we talked about, on-prem, co-located, all the way to cloud, right? So now we hopefully have a picture of the way companies utilize IT. How do we think about cloud security? We need to know and take a step back and be a little bit more general before we get into the cloud and just talk about information security. I don't know if this is talked about in your cloud, but I will advise everyone here, unequivocally, if you're going to be anywhere in the cybersecurity space. There is something from 1975 called The Protection of Information in Computer Systems by Salzer and Schroeder. It's about a 10, 20-page research paper that identifies 8 design principles. I'm going to make a claim that there's 4 key contributions that came out of this research paper. And you'll see in a minute, and I think you'll say, I know what that is, without knowing what this is. But this is the foundation of all information security, and very specifically cloud security. So Salzer and Schroeder were these 2 gentlemen that you see on the screen here. They were the authors of this paper. And the 3 key contributions that came out of this, number 1, they provided a framework, a way for if you were to start a company and you said, I need to protect my company. And you said, okay, I'm going to have a security guard sit out front. I'm going to have cameras in the building, right? You thought about these things. You thought about physical security. And in the early days of compute, that's what was protected. I think we've all seen those pictures when computers were the size of rooms, right? They were very, very big machines. There was a big investment in the hardware, in the physical. But somewhere around the 70s, what happened here is people said, well, wait a minute, the data is actually more valuable than the hardware. And today that's true. If somebody stole this DIMM here, this DIMM is today, this is probably $50. I'm out $50. What if this data here was the results of an election? What if this data here was your keys to your Bitcoin? Invaluable. The $50 price of this silicon is nothing compared to the data. And this realization came about in the 70s. So this second point, focus on information. This was a revelation back then. And I'm really sensing a lot of people now hesitation putting things online, right? Because we're all starting to realize what's the importance of data privacy and understanding like, gee, maybe I really shouldn't be putting all those pictures out there, right? And in some cases, you're not even putting stuff out there. It's getting leaked, right? How many companies get hacked and all of a sudden your phone numbers, you're on some call lists from somewhere. I don't want to get into that. I've had some bad experiences, but your data gets leaked, it gets breached, right? Way, way, way more impactful to me than if this DIMM broke in my home computer. Lastly, I mentioned this, their work was actually instrumental in operating systems as well. So how we knew when I'm running my banking app on my computer and then I'm running Netflix in my other tab, how they don't intersect, right? I think we could all agree, for whatever reason, I wouldn't want my banking data to be sent over to Netflix when I'm watching the fight. So where do we see Salzer and Schroeder's work? Are people familiar with these? Are these terms that I'm throwing up familiar to people in this space? Is there anybody here who works sort of in a compliance space that may have seen these? Yes, please.
Yes, I did like some risk management work for like internships, and we've talked about GDPR and this.
Yeah. So GDPR is regulation in Europe, basically saying, hey, data in Europe has to stay in Europe. They are trying to protect their European citizens. I think fair transparency from the US, they're trying to avoid the FBI from seeing data on people in Europe. But then we have other things like SOC certification, SOC 2. It's an accounting standard, believe it or not, but it ensures that your data is protected appropriately. ISO 27001, it's called an information security management system. How can you prove to the outside world that you have good security practices? You do disaster recovery. You have a pandemic recovery plan, right? Things of that nature. So any certification that you are ever going to see has the foundation in the 8 design principles of Salzer and Schroeder, which we're going to look at now. So when we're securing an IT system, number one, economy of the mechanism, do the simple thing, okay? If you end up building a security solution and you spend more money and more time to keep the security system up and running, it's not worth it. So if you know a lock on your door at your house is going to keep out 90% of the intruders, do that rather than trying to get a howitzer, which is a big gun, right? And put it in your front yard and have somebody man that howitzer, right? Sure, that might be more effective, but now you got to pay for the gun. Now you got to pay for the person in the front yard, right? So there's a lot of reasons why you want to keep things simple. Number 2, fail-safe defaults. Let's be pessimistic. You know what? If we're not sure if you should have access, you don't have access. We have to be careful with this because this does have some real-world ramifications, right? Think about the idea of a building and when there's a fire, right? If there's a fire and the power goes out, you don't want all your doors to lock. That could be a big, big problem, right? So we need to make sure they're potentially locked from the outside, but not the inside. But even that might be a problem in a situation like that. But generally with our software, if we're not sure if you should have access, you shouldn't have access. Complete mediation, right? So every time somebody wants to access something, you should check. So I don't know how many people here, work out in industry, but presumably, a lot of us have badges, right? And when you want to get into the building, you badge into the building every single time. If you're trying to get into the server room in the building, you should badge into that server room as well. If you're not supposed to have access to the server room, if you're not supposed to have access to the IT closet, if you're not supposed to have access to where electricity comes in, then you should not have access. So when you go to that door with the IT closet, you should have to badge. Open design. I'm not sure how much y'all talk about things like cryptography, but certainly we've seen the effects of this in our industry with things like Linux. Linux is an open source operating system. What does that mean? every single person in the world can see every single line of code. You can see everything that's flowing through that machine. And so you can detect if there was malfeasance. You can detect if there was a mistake. And you can very quickly see, oh, we got to correct that. We've got to change it. And so we see this a lot with things like cryptography. When we talk about AES encryption, right? When we talk about RSA, those algorithms are public because the strength of the algorithm is not in its secrecy. The strength of the algorithm is saying, look, somebody prove me wrong. It's like my statement when I started this chat. If I say something wrong, please chime in. Let me know. Be like, Fulton, that's a little bit out of bounds. That's not right, right? We should all be very open and transparent and say, look, it's not a secret here. I'm not saying to you, just trust me, everyone. This is how cloud security works. Hopefully, I'm giving you the foundations here to make that decision yourself. But this plays into the cloud because in the cloud, where I have Amazon well, on Amazon, I have Netflix running and I have my shopping app running and I have this video app running, right? If one of those had a security flaw or security break-in, other people should know about that. They should know what went wrong and how to fix it or how to prevent it. All right, separation of privilege. Kind of this example of the badge here. The person who's going to physically give you this badge, take your picture and give you this badge, probably shouldn't be the same person who's giving you access to the server room. Those should be two separate people. And so again, in the cloud, this is now all virtualized. So the person who gives you access to use Gmail, that should not be the same person that gives you access to the data center to walk in and pull the disk out of the rack that has your data in it, right? It should not be the same person. Least privilege. This is going to come up in a minute in a more expanded example for everyone. But I kind of mentioned this before. Only give access to what you need access to. So if you don't need access to the electricity closet, don't have access to it.
I have a question.
Yes,
For
please.
the fail-safe and the least privilege, do they go hand in hand?
Ooh, that's a very, very good question. In some cases, they do. And so you want to say to yourself, that secure room in my office that has all the files or it has the HR records, right? Do I want that door to open up when there's a fire, right? And again, you have to ask yourself that question. Well, I probably do. Like, what happens if somebody happens to be in there when there's a fire and the power goes out of the building? So these are considerations that you need to think about. And in the cloud, you need to think about it virtually, right? It might not be the person is physically in danger like that situation. But if, how do I put it? That virtual program that's running that has your banking application, if it loses network connectivity, should you be able to call up a help desk and someone who's sitting in the data center be able to access it? Maybe. But if that person who's in the data center is the person who runs around swapping disks, maybe not. Least common mechanisms. This one's kind of interesting. This one is a little bit about, limit what users share. So do I want to have 100 customers on one machine, right? Maybe that's too many. Maybe I want to isolate them a little bit just so I know if there's a problem with Dan's nodes, like his computer they were all jacked, right? There was a security breach. I know these 3 physical machines were compromised. It's not every single machine in my 10 million machine arsenal in my data centers. Last one, and to be honest, I probably should have put this as the first one, psychological acceptability. What does that fancy word mean? Do people know what they're doing, right? Do people accept that, hey, listen, I can do this stuff, right? So we can all agree we know how to put a lock in our door and open it. That's not a big deal. It's a little bit harder when it's a keypad, but maybe not the worst thing in the world. But if you have some homegrown system where you have to type in the keypad and simultaneously put your key in and put your foot in a certain place and have your eye in the retinal scanner, people might say it's not worth it. And what are they going to do? They're going to come up with workarounds, right? And they're going to say, okay, I'm going to put a picture of my eye on my phone and I'm going to hold that up and I'm going to, it causes more problems. So we need to always consider the user first, right? Are they going to accept these things? How do we make it so a human, because a human is the biggest failure point in any of these systems, how are we going to make them be receptive to doing all this good stuff? Okay, a little knowledge check here again. We talked about 3 deployment models for the cloud: SaaS, PaaS, and IaaS, right? And so SaaS was like Gmail. PaaS was like, I provide web servers and you can put your own web application on there. And IaaS was like, hey, you have access to the physical machine, do what you want. So when we think about that, how do we think least privilege manifests in these different cloud deployments? What do we have to think about?
For infrastructure, I think least privilege would be like the thing with the badge, where it's like if you don't need access to that room, you won't get it. For platforms, since they are giving you access to the cloud and you put your own platform, it's like, okay, there's certain things within that you can't do or can't go into. And in software, as like with Gmail, you can like change your name and do all this stuff, but there's a limit to what you can do on their actual software.
Wow, yeah, that's great. Yeah, those are great examples. Anybody else have any thoughts on this? I mean, I'll flash it up. That's great. I think you summarized a lot of these. So when we think about something like SaaS, if we take Gmail as an example, right? When Brittany gets access to Gmail, she has access to her email account. She doesn't necessarily have access to the instance that she's connected to in Greensboro, right? She can't go in and say, "Ooh, I can look at the database where my email is stored." Yeah, sorry. Yes, it is your data. It is in that database, but I'm not giving you a SQL connection where you can go fetch that data. PaaS, that's sort of the software as a service. So if I'm going to say, hey, listen, you know how to run your business, you sell shoes. You know how to run your business, you provide, advice on accountancy, whatever it is. You don't know how to set up a web page. Cool. Here's WordPress. They take care of everything else for you. You can generate your web page as if you were writing a Word doc, and bam, they will host it. Here's a domain name, and I can do danshouseofshoes.com. And what are some of the common features? Well, maybe, right, they say, hey, do you want people to log into your site? And you're like, actually, that would be a very good idea because I'm going to take credit cards or I'm going to store personal information. And so there might be a common way to log in. And maybe we've all seen that technology, OAuth, right? So like it's like the Google login. You go to some random site that's not Google and it will say, do you want to log in with your Google credentials? Google's basically vouching for you. Google's telling these companies, hey, listen, I know that's Brittany because Brittany gave me her password and her 2-factor authentication, and she told me you said it was okay for me to let you in. So now you can access this site. So that's the idea of PaaS. And then IaaS it says it's complex is because now you're kind of into the physical world. So if you're going to say to somebody, hey, listen, you can use our hardware at the fundamental level, or you can use the bare metal. Oh, by the way, you're not exclusively on that machine, right? We have a customer who's using our SaaS service, Gmail, and some of it's running there too. If you have this sort of like core access to the processor, take my Linux example again. If it's running Linux and there's a 0-day that comes out and you exploit it, not only can you exploit your workload that's running, but you might exploit all this other stuff that's working on that bare metal or that virtual machine or hypervisor, which is the layer above that. All right, cool. This one, I did put some time into this in the notes. There's a whole bunch of examples for each of the 8 Saucer design principles. So if you're interested, have a peek at that. Okay. We can all agree memorizing less things is better and easier. So if you can't remember the 8, we'll distill it down to 3. A lot of times when we talk about information security, we talk about the CIA triad. And so when we're protecting information, we're primarily worried about 3 things. Confidentiality, right? Who has access to my information? How is it being protected, right? Integrity. How do I know if it's been tampered with, right? And availability. Can I get to it? And so, the great sort of classic example is sort of hospital systems, right? Confidentiality. You don't want everybody at the hospital having access to your healthcare information, just your provider, just who's working on your case. Integrity. You want to make sure that if it's the doctor or the nurse practitioner or the nurse or whoever that's putting in the information, that they put in the right information, they had access to the right information. It wasn't someone who's working in the cafeteria that happens to have access to your account where you put your credit card. They should get your credit card information, not your healthcare information. You can see where you can get some blurred lines, right? Maybe you have some nice, valuable information in your healthcare records, like what you're allergic to. And when you go to check out in the cafeteria in the hospital, wouldn't it be great if they said, well, wait a minute, you grabbed the, pecan salmon and you're allergic to nuts, right? And so you could think there's really good reasons why you might want to have that integration, but really, no. I'd rather take the chance than them accidentally seeing my health records. And availability. Our information is worthless if we can't get to it, right? And so this is where things like disaster recovery become a big, big deal. What happens if your data center's in Tampa and a hurricane hits it, or the second one, or the third one, or the fourth one, or the whatever one we're up to this year so far, right? It would be nice to know that if there's an issue there, your data can be running in a data center in, Idaho. All right. This is where this goes from being an undergraduate course to a graduate course, in my opinion. Hopefully this is some value I might add that you might otherwise not be privy to. Not that this is a big secret here. If you want to be a good cybersecurity person, know CIA, right? Know what that means, know how to implement controls to keep data safe. If you want to up-level it a bit, consider the following. Because again, this is important for the cloud. CIA doesn't talk about possession. It doesn't talk about control, right? To a degree, you say, I want my data to be available all the time. I only want certain people to change it. That's my integrity. And confidentiality, I don't want people to see it who shouldn't see it. But it doesn't really say, is this in your own building? And so a cloud, honestly, you really don't know where your data is. You might know and configure it to work in a data center in New York, right? But maybe that data center backs up its own data to Pennsylvania. And for whatever reason, you had data that couldn't leave the New York State jurisdiction. That could be a problem. So we need to consider possession. Where does our data sort of reside, physically or logically?
Would that be like a geolocation like setting, or would that be something you do on like your router, your switch?
That's a big part of it. A great example that I've used this at work a couple times before. So let's say you're a hyperscaler and you're servicing a public sector customer, a government, right? Let's say that customer is the US. And so there's a regulation called FedRAMP, and the FedRAMP might say, hey, listen, this data can't leave US. It can't be routed to Europe. And you say, okay, well, I have a military base in Hawaii and I have a military base in California, and I want them to talk to each other. And you can say, okay, well, we're going to route the traffic between A and B. And so typically that data is going to go from Hawaii to North America. I don't think there's a subsea cable going that route. So somehow it's going to get routed there, sort of virtually. And maybe the most expeditious route is to go directly from California to Hawaii. But what happens if there's just latency on the internet and your data gets routed through Asia, or it goes the long way around through Europe? Even though your data might be encrypted in transit, it technically left the US, right? And so do you know that? Are you aware of that? Can you set up your routing tables to say, listen, this data's got to take this particular route, period. If there's no route through these points of egress, then do not route the data, just fail the traffic. Very good, astute question. Authenticity, origin of the data. Hugely important in this day and age of AI. AI wouldn't exist without data, but do we trust the data? Do we know where it came from? CIA doesn't talk about that. CIA doesn't, it says, yeah, your data is confidential. Yeah, we can guarantee this data wasn't tampered with. Where'd it come from? Did AI generate the data and then some other AI used the data and all of a sudden it became factual, right? So authenticity is something we need to consider. Finally, utility. More data is not better. Just because you have more data, I think there's some companies like Reddit that are, well, obvious, they are a gold mine, right? Because people freely gave them all this information. So in that case, more data was better. But if you're a business, more data is not better. I'm not sure if anybody else here is paranoid like me, but my tax returns, when my accountant says shred them, I shred them. I'm not talking about last year's, but I think it's like 7 or 8 years, you shred them. Having that data around is not doing anybody any favors but you, right? So we have to understand what is the purpose of our data, what is the intent. If I am setting up a website for a concert I'm putting on, and I never intend on having another concert again, if I captured all these credit card details for credit card payments for my concert, get rid of them after the concert's over, unless I'm going to have another concert, right? But more data is not better. So we need to consider that. All of this is codified in something called the Parkerian hexad. And it's also kind of cool to say. So if somebody's blabbing around about CIA, you can throw out Parkerian hexad and you can sound really cool. Parkerian hexad is just the CIA with 3 other points into it. So dropping that knowledge here. Okay, so let's do a little knowledge check. Let's do a little thought experiment, right? So imagine a secure document storage system. Gee, I don't know, like Google Drive, right? Google Drive, I'm going to store my documents on there. Google Drive doesn't really care what that data is. And it's actually very interesting from a security perspective, a compliance perspective. What happens if you're storing copyrighted information on there? Okay, you probably want Google to prevent you from doing that, right? Well, that means they have to look at your data. What happens if you're storing your health records on there? Do you want Google looking at your health records? I'm going to argue no. So imagine we have a secure document storage system. It's secure. Only you can access it. You determine who you share it with. Okay. So Salzer and Schroeder's principles would guide the design of the access controls in integrity. What would the Parkerian hexad add to this decision? So the 3 elements of the Parkerian hexad: possession, authenticity, and utility. So what would we consider that we didn't consider with those base 8 design principles with possession?
That the data is going to or stored where we say that it is.
Yep.
I don't know how that would work with Google Drive if they don't check. Maybe if you say like, oh, I'm saving it on my computer on this part of the folder, I don't know. I'm trying to pull something. I have no clue.
No, look, that's a great thought. You as an individual, you might not have a say, right? But what if you were a company? What if you were the US government and you said, hey, listen, we want to use Google Drive to store our files. But guess what? We don't want that data going to your data center in Saudi Arabia. We don't want
I was in the military, so we kind of had something like that when I was in the Marines. So even though we're under the Department of the Navy, we had like our own subgroup within the cloud. And so that's where, and then all those subgroups would have like different like bases that would keep breaking down. So you'd only be able to save it in that part and you weren't able to access anything from like another units, even if like you're on the same ship or something like that.
Exactly. That wonderful example. So authenticity, right? So I'm storing my data there. The best example I can give that, and there'll be another example that pops up here, but your data is probably being copied around, right? We don't want to just have one copy of your data. Copy of my data is probably living on some server in Raleigh. But there's a backup. There's a backup of that data that's living out over in Denver, right? In case the Durham data center blows up, something like that, right? Well, how do I know Google copied my data word for word, right? And hopefully you've learned a little bit in this class, things like hashing, right? You put by hash it,
cryptography.
say, hey, cryptography, yeah, use any sort of mechanism for that. All right. So anyways, you can take a peek at this. Let's get on to our last and sort of, now that we have this foundation, right? hopefully we understand how IT is deployed. There's a lot of different mechanisms, and cloud is kind of just an instance of colo, right? It's like colo with value add, right? It's not just the physical stuff, but it's also the rapid elasticity. I can charge people for it. On-demand self-service, my customers can add nodes, they can remove nodes, they can add storage, they can delete storage. So how do we take that, map it to general information security, which we just looked at, and apply them, put those two things together? Cloud security, our core topic here, okay? This is my, just in case we were running late slide, I wanted to put this all in here, but we'll walk through these. I think we have a little bit of time. What are the unique challenges? What are the things?
Not too much time.
How much time do we have left?
5 minutes.
5 minutes. Cool. All right. We can get through. Yeah, 8 is in 5. That's cool. So the unique challenges here, shared responsibility model. So we have to think to ourselves, okay, this machine might have 3 customers on it. This data center might have 1,000 customers on it. Some of them might have access to the CPU. Some of them might only have access to a virtual machine. We need to think about those things. Threat landscape. I mentioned this before. Our stuff is running underneath the ocean, right? That's now a threat. What if somebody cuts those cables, right? So expanded threat. Somebody can get my data not just by breaking into a building, but tapping into a cable undersea. It sounds far-fetched, but I really don't think it is. Data location and control. There's examples about like the military, right? That data for whatever mission purpose needs to be in a particular location and nowhere else. Visibility. You don't typically have access to the physical plant your data's in. How can you manage your data, right? So we have to think about that. The elasticity. That's not a concept that generally exists in a non-cloud environment where you can virtually start up a machine and set it down. Typically, you're putting hardware into a rack. Compliance and auditing. I gave a couple of examples about like HIPAA. If you're a hospital and you're using, you're storing, patient data, if you want to be HIPAA compliant, I guarantee you there's physical controls that have to be checked. So that auditor that's auditing Aetna probably wants to go into Google's data center and say, prove to me you have cameras. Prove to me you have locks on the doors. In summary, cloud security, we have to think about these 3 things as opposed to these other deployments of IT. So we have shared responsibility. We need to make sure the IaaS provider is going to do something, the PaaS provider, the SaaS provider, the customers. We have to understand that we need new tools. We need new technologies. We need to remotely connect. We need to use virtualized servers, something we might not have done before. And lastly, we need to just constantly adapt. Because of the ubiquitous nature, the fact that we have networks all over the world connected to these data centers, we need to constantly monitor that, and we need to be ready for the next threat, right? We need to be ready for the next technology that comes in. The last stuff I'm going to get to here is just, you want to know what a job is like at Google. From an organizational perspective, these are the organizations we have. Sec engineering and operations. These are the people who are physically writing the code that secures the software. Product and application, they're doing kind of the same thing, but maybe at that SaaS level. Data security and privacy. Forget the physical plant stuff. Who's dealing with the actual data itself? Threat intelligence and research. At least at Google, we bought a company called Mandiant a few years ago. And so how can we do proactive understanding of what the landscape is outside here, outside the company? Classic GRC. Most companies will have this. Governance, risk, and compliance. Are we taking too much risk? Are we not taking enough risk? Does this risk, are we going to breach PCI DSS if we're holding credit card data? Last one, which is kind of interesting, is customer trust and security. It's a shared responsibility model, right? What are our customers seeing that we're not seeing? So I'll leave these. You can look at those in more detail. I'll leave you with the last 2 slides in the last moment or two here. These are the actual roles. If you were to say to yourself, hey, I'm looking for an opportunity in cybersecurity, what might I be able to do? These are some of those job opportunities here. Very few of them say, hey, you have to be a computer science major with an ability to code. That's very useful in a lot of cases, not necessarily useful for all of them. So some resources for you. This slide here, this is very, very interesting. This should be launched in the next week or two. It's called the Career Dreamer Platform. Long story short, you start out, it's an AI model. You go in and you say, I'm interested in a career in cybersecurity. It will ask you a few questions. Are you interested in working in a building? And it might say you want to go work at a NOC in a data center, but it'll work you down a path. I played with it, a little prototype. Very, 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 very interesting. If you are looking for some outside of the classroom opportunities, there's something called Grow with Google where you can get cybersecurity certificates just to reinforce your knowledge. A lot of the foundation here are for something called CISSP, which covers these 8 domains. Ironically, if you go back and look at those job opportunities at Google, if you go look at the organizations, they kind of map to this. So a cybersecurity professional would have some capability in all of this, but sort of like an inch deep, mile wide sort of a mindset. All right, so I'm good with staying on time, Ken. That's where we are. I have some just takeaway articles, some videos from other cool lectures and stuff I pulled together to get my material here. Any last minute questions here?
This material is in the slides that we put out at Blackboard.
Yes, sir.
Great.
Are you teaching any classes in the spring?
I am not teaching classes in the spring. We'll see about future opportunities for Dan. I got to go back and do my day job for a while.
Well, thank you very much. Anybody have questions for Mr. Fulton? Well, I'm going to just take a couple minutes here to review for the exam on Monday. So I'm going to see if Dan would stop sharing the screen. Okay, I will go.
Did that unshare from you there? There we go.
There we go. Okay. Then, exam 3, a couple real quick. Yes, we just talked about cloud security on Monday. That's like Monday. It's next week. What is that? 5 days from now, we have the next exam. A week from today, of course, Thanksgiving break. And then look at that. Final exam. The end is near. Oops. Exam will be just like all the others. Open book. Answers no more than 75 words unless the question says you can. And it's be open at 6 a.m. till midnight. It should not take you 18 hours to answer the exam, but you have that much time. There will be no lecture on Monday, November 25th, when the exam is going on. If at any time you have a concern, question about the exam, just call me, email me, text me, and we'll make it work. We'll figure it out. Okay. Get that. Okay. Topics. You could see this from the syllabus. This is what we've covered. It's going to cover only material from after the second exam. Now, that doesn't mean you can forget everything from before the second exam, because sometimes some of the solutions we have require you to know the material from previously. Some solutions require some sort of encryption. Well, you better remember the encryption stuff. Okay, and there are the chapters from the textbook. Same thing from the syllabus. Okay. Reconnaissance. Dr. Ravel talked a little bit about reconnaissance. The reconnaissance, again, is understanding what the victim is, looking out to find out what do they have, what systems do they have, what networks do they have. There are several ways you can do that. There's a ping tool. It's very simple. Just ping space web name, and it will tell you the IP address and how long it takes to get there. How long it takes to get there isn't so interesting, but it tells you the IP address. So WHOIS, there's several websites that do WHOIS. There's actually Unix utility that does that. You just give it an IP name or an IP address. You get different results from giving them different ones. So you might want to try both. And of course, as a defender, you want to make sure you don't give out too much information. I tell you this because you can probably look forward to a recon question on the exam. And again, there's all sorts of places where you can find information about it. Intrusion detection systems. Dr. Val talked about IDS systems, looking for trouble. Overflow. We talked quite a bit about overflow. guess there's integer overflow. Again, here's my example I used before. If you give it a great big number, what happens? You add 5 to that great big number and you get a negative number. And of course, the negative number will appear to be true in this equation, but a real positive number will not. So, oh, yes. So there, again, that would not work if they give a great big number. So, gotta avoid that. Stack. Watch out for stack overflow. We talked about stack overflow real quickly. Again, you push the values on the stack, including the return address, the frame pointer, not too important what that is, and then local variables. If a program goes past the end of the local variables, it starts putting data into the frame pointer, into the return address, into the other values. The return address is of particular interest because you can change where the program is going to go when the function returns. It will go someplace else. By putting in careful values, putting them into that array, you change the return address and the program will do what you want it to do, not what the programmer intended for it to do. Stack canaries are a way of protecting against that sometimes. Stack canary goes after an array when the user accesses the array. If they go 1, 2, 3, or 0, 1, 2, 3, 4, the 4 will step on the stack canary, and then when the system checks the stack canary, it's, oh, it's not what it should be, and it will stop your program because there's been an overflow. This might have changed the return address and other values. We don't want to risk it. It'll just stop your program right there. So that's a stack canary. Many things you can do to prevent this. Again, some languages don't allow this. Some languages like Java and C# check everything. I'm not sure about Python, but it might also check that. Randomized stacks, there's a list. We talked about those when we went over stack problems. Forensics, yes, forensics evidence. There are the 5 rules. We went over them in detail in that lecture. And remember, of course, the exam is open book, open web. You can go back and look at the slides on Blackboard. You can rewatch the videos or watch it for the first time, perhaps, and make sure you understand this material. And there's a forensic process. We've talked about that before. Privacy, we talked a little about privacy. We had a whole lecture on privacy. And again, it is cultural. It depends on what you believe to be private. Some people are very concerned about certain aspects of their life being private. Others don't care at all. They'd be happy to tell everybody and anybody. So it differs between people. Of course, that means in a privacy system, you need to tailor it to people's needs. Denial of service. Denial of service is when you do something to keep other people from using that resource. There are all sorts of ways to do that. I'll get that. But basically, denial of service is not. Distributed denial of service is commonly used. You use lots of computers like a botnet to go out and get this. Several ways to do that. Consumption resource. You use up the CPU, the network bandwidth, all some sort of disk, memory, file space, network, using some of those resources. And once you do that, you stop the system. Of course, you can also cause programs to fail. If you make the system crash, if you cause that program to get an error and stop, well, you've done denial of service. And there's many other ways here, along with the physical ways. We talked about sync attacks. That's also sync floods. Those are a possibility. Election security. You need to make sure you keep the system safe. There's all sorts of malware out there. You should understand the difference, what they are. Trojan horses. Trojan horses is a program that's built with something inside of it. Not only does it do the task you asked for, but it does something malicious. Computer viruses, the big thing about a virus is it propagates itself. It modifies other executables so that they do something evil. It copies the virus into other executables. So it propagates all over the place. Computer worms propagate. Computer worms are a little different than a virus. A virus is a program kind of like a Trojan horse where it does something that you want, but it also does something evil. A worm is just evil all over, and they propagate around. Rabbits, this is a denial of service attack where you try to consume a resource. This is where we're going to consume the CPU and the number of processes. Operating systems typically have a limited number of threads that can be going on. Oh, there's often hundreds of threads out there, but there's usually a limit of, say, 65,000 threads that can run. If you start more than 65,000, the system will not behave well. Botnets. Botnets are used for denial of service. They're where you go out, or an attacker goes out and infects a machine with some software that will then do what the attacker wants. You might get lots of these computers that are infected, and then at the appropriate time, all these thousands of computers attack the victim. Phishing, yes, we all know about phishing. We've received many phishing messages ourselves. Phishing is one of the great dangers because it's used to start all sorts of other problems. Found thumb drives is another way. And that's it. Do people have any questions about the exam on Monday? Well, hearing none, great. You're all ready to go. I'll be ready for the exam. If you have questions, do email me, call me, text me, whatever, and we'll figure it out. Okay, good luck on that exam. Bye.